In this video, we're going to look at an example context-free language and design a grammar for it. In fact, we're going to look at two different grammars for the same language. Here's the grammar we're going to look at. We'll present this as sort of a challenge. After I describe the grammar, you might want to pause the video and see if you could come up with a context-free grammar to describe this language. I think that exercise is very valuable, so I encourage you to try it. Okay, here's our language. It consists of the strings drawn from the alphabet of 0 and 1, so strings of zeros and ones, such that the number of zeros is equal to the number of ones in the string. Okay, so you might want to stop the video right now and give this some thought. Can you design a grammar that will accept the set of strings of zeros and ones where there's an equal number of zeros and ones in the string in any order? One approach you might try is to try to think of meanings for the non-terminals. What does each non-terminal mean? Or what are some possible meanings that you might want for this grammar? So, in my solution that I'm going to present just in a second, we've got three non-terminals, S, A, and B. S is a string of zeros and ones where the number of zeros and ones is equal. Okay, that's the language we're looking for. That's our starting symbol. Okay. The strings described by the non-terminal A will always have exactly one more 1 than zeros. So they've got essentially a deficit of zeros. They need an additional 0. Likewise, the strings that are generated by non-terminal B will have one more 0 than ones. So they've got a deficit of ones. Okay, now let's take a look at these rules here and see if we can understand how they work. S is our starting non-terminal, and we have three rules for that. First of all, the empty string is certainly a string that's in our language. The string either begins with a 0 or a 1. Okay? There are no other choices. So if it begins with a 0, then the rest of the string has a deficit of zeros, and it needs to have one more 1. Okay, so it needs to have an extra 1. So we need an A. That's the way we defined A, is that it's the set of all strings that have one more 1 than they have zeros. On the other hand, if S starts with a 1, then we've got an extra 1 and we need an extra 0, so we need a B, which is the set of all strings that have one more 0 than ones. Now let's look at how we define A and B. A can either start off with 0 or 1. B can either start off with 0 or 1. A will expand to a string that has one more 1 than zeros. Okay, if A starts with a 1, then we're done. We've got our extra 1, and then we can follow it with any string where we have an equal number of zeros and ones. On the other hand, if A starts with 0, well, A is supposed to have one more 1 than it has zeros. So now we've got a double deficit of ones, if you will. So we need to have two A's to pick up two additional ones. B is structured similarly. It either starts with a 0 or a 1. B is a string. B expands to any string that has one more 0 than ones. So if B starts with a 0, we've got our extra 0 already, and we ought to have a balance of zeros and ones in the remainder. So we use S here. On the other hand, if we get a 1, then we've got to pick up two extra zeros. So we have two B's. Okay, two strings, each of which has one more 0 than it has ones. This language is somewhat interesting because it has two grammars that are somehow different, but that describe the language. So this is an example of a context-free language with two relatively different grammars that can describe the same language. So here's another context-free grammar that describes the same language, where you have the same number of zeros and ones. Again, we've got three non-terminals. In this case, A goes to something that has a 0 and a 1 in it, and so we know that the numbers of zeros and ones are balanced here. B goes to something that has a string that has the same number of ones and zeros. S is a string that has the same numbers of zeros and ones, so when A goes to this, it must have the same number of zeros and ones, and likewise for B. And they can all go to epsilon. Now, how can we understand this grammar better? First of all, I want to look at this pattern. S goes to SAB or S goes to epsilon. This is the general pattern. Here we see a left recursion version of this. Okay, we've got some non-terminal going to a right-hand side that starts with that same non-terminal and some other stuff, or epsilon. Okay, X can be a single thing or several things, whatever X is. This rule, or these pair of rules, generates a string of 0 or more X's. Okay, epsilon, or we can use the rule once and then let the C go to epsilon, and that gives us 1X or 2X's or 3X's and so on. So when we see this pattern, either with left recursion or right recursion, we know we've got a string of 0 or more X's. So if we look up here, we see that pattern. We've got left recursion, we have a string of 0 or more AB pairs. So these two rules generate AB, 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 AB. Now notice that with these rules, every A can go to an epsilon, and every B can go to an epsilon. So basically, we're left with we can derive any string of A's and B's that we want. Okay, any arbitrary string of A's and B's. So, for example, we might have a string of just all A's, and then we can expand them using this rule, using the rule for A, that A goes to 0, 1. And we could get the string 0, 1, 0, 1, 0, 1. Another way to look at it might be this. Everywhere we have a 0, it's got to have a matching 1. And between them, it has to be a string with matching zeros and ones. And so that's another way to look at what A might do. So these show two different strings that we can generate with this grammar. They're both different, but we can see that this is a second grammar for the same context-free language.